All right, let's jump right in. The paper we're diving into today is video generation models are good latent reward models. And it immediately gets to the heart of one of the biggest computational headaches in video synthesis.
It really does.
We're talking about reward feedback learning, or ReFL. It's totally crucial for aligning models to what we actually want. But when you apply it to video, it just hits a computational brick wall.
A massive one. And that wall exists because the traditional approach, what you'd call outcome-based ReFL, it has to operate in RGB, the pixel space.
Right.
Which means you are forced into this incredibly expensive step, VAE decoding. You have to translate the model's internal language back into pixels just to see if it did a good job.
And for a full video sequence, that means decoding and then backpropagating through that decoder for every single frame. It just creates this insane GPU memory overhead.
Yep, you're hitting out of memory errors left and right. It just doesn't scale.
And the most critical part, I think, is that this feedback comes way too late. By the time you're giving the reward to the final clean video, you've completely missed the chance to guide the early stages.
Exactly. That's where all the important stuff happens. The core motion, the structure of the scene, that's all decided early on in the denoising process.
So this paper's solution is really elegant. It's called Process Reward Feedback Learning, or PRFL.
And the core idea is that the video generation models themselves, the VGMs, are already built to be great reward models. They already understand good motion, and they work natively in that noisy, latent space.
You're taking the reward function and moving it inside the model, basically.
You are. And the results are, well, they're pretty transformative. By doing everything in the latent space, PRFL saves a ton of memory. We're talking about processing full video frames that the old RGB method couldn't even touch.
And that leads to huge speedups and, more importantly, much better quality. They clock training at over 1.4 times faster.
And the alignment with human preferences just shot up. We saw these massive jumps in metrics like dynamic degree, which is all about motion quality, up by 56 points.
56? Wow.
And human anatomy coherence, up by over 21. It's a huge leap in both efficiency and quality.
Okay, so let's properly unpack that core problem. We're at a point where VGMs can generate photorealistic stuff, but there's still this quality gap, right?
Oh, a massive gap. It's in the subtleties, physically believable motion, making sure a person's limbs don't do something weird, just general consistency.
And traditional methods just aren't built for that because they rely on these separate vision language models, or VLMs.
Right, and VLMs are designed to look at clean pixels. They have no concept of the messy, noisy process that created them.
The paper points out 3 big limitations here. The first is just the delay.
The evaluation delay, yeah. The VLM needs a clean RGB video, so the model has to do almost all of its denoising work before you can even start to tell it if it's on the right track.
So you're just burning compute cycles waiting.
A lot of them. Then you hit that GPU memory bottleneck we mentioned, and I think it's worth explaining why that happens.
Go for it.
So when you backpropagate, you have to keep all the intermediate calculations, the activations in memory. The VAE decoder is a big network. Now imagine holding the activations for that entire network for, say, 80 high-resolution frames all at once.
Your VRAM just gives up.
It just says no. It's a hard physical limit that prevents the old RGB ReFL from working on full-length videos. It's fundamentally broken for this task.
And that third limitation, the insufficient supervision, feels like the most critical one conceptually. The reward only comes at the very end.
It's like trying to coach a basketball player by only watching their final shot. The footwork, the setup, the entire motion, that all happened way before the ball left their hands.
So that late-stage reward is trying to fix a problem that was locked in dozens of steps earlier, back when the image was mostly noise.
Exactly. So the mission becomes clear. You have to move from this outcome-based reward to process-level supervision. You need a reward signal that's active throughout the whole journey, from noise to final video.
Which brings us to the big question. Can you really trust the video model to grade its own homework? It feels a little counterintuitive.
It does, but VGMs have these built-in advantages. For one, they are already noise aware. They were trained to understand and operate in that noisy, latent space.
They speak the language.
They speak the language. They're also super sensitive to generation artifacts because their whole job is to remove noise and create coherence. And of course, they naturally support full sequence video.
The paper really proves this with data. They show that a traditional VLM like VideoAlign MQ Just falls apart when it sees noisy inputs. Its performance is all over the place.
It has no idea what to do, but the VGM's internal features are incredibly robust. They tried probing features from all these different layers of the model's core, its DIT blocks.
And even with just a simple little MLP probe,
They got a baseline accuracy of almost 79%.
that is shockingly high. It proves the information about what makes a good video is already there, baked right into the diffusion model's brain, no matter how noisy the input is.
The signal is there, but here's the twist, the real aha moment. Just probing the features wasn't quite enough.
Right.
The breakthrough came when they combined full fine-tuning with random time-step sampling.
Okay, hold on. Full fine-tuning sounds expensive. Isn't that a big hurdle?
It's a cost, for sure, but it's what's necessary. The task isn't just to read the features, it's to teach the model how to weigh them all and combine them into one single coherent quality score. A simple probe is too local.
Ah, I see. So the fine-tuning teaches it to see the bigger picture across the whole sequence.
Exactly, and that combination unlocked its potential. The accuracy shot up to over 85%, and the strongest signal came from those early noisy states around t equals 0.8.
That's the proof. The guidance we need is right there in the noisy latent space where it all begins.
And with that proof, they could build their process-aware video reward model, or PAVRM.
This is where it gets clever from an architectural standpoint. How did they decide which part of this giant VGM to actually use?
They went for efficiency. PAVRM only uses the first 8 DIT blocks of the pre-trained model.
Just the first 8.
Yeah, their analysis showed that the most important information for quality, the core structure, the motion plan, it's all concentrated in those early to middle layers. You don't need the whole thing.
And they still have to solve the problem of video length.
Yeah.
How do you get a fixed size score from a variable length video?
This is where their query-based spatiotemporal aggregation comes in. It's a really neat trick. They introduce a single learnable query vector.
A Q vector.
Right. And they use an attention mechanism. You can think of this query vector like a single question you ask the video. On a scale of 1 to 10, how good is your motion quality?
So no matter how long the video is, the model is forced to compress all its knowledge into the answer for that one question.
Precisely. It encourages the model to learn abstract quality patterns instead of just memorizing content. It's a very smart way to enforce abstraction.
And for the training objective, they went with binary cross-entropy loss. I was a bit surprised they didn't use Bradley-Terry, which is pretty standard for this stuff.
They found BCE performed just as well, if not a little better, and it was cheaper computationally. It avoids the whole headache of creating preference pairs in your batch.
Another win for efficiency.
But the real secret sauce, the thing that makes it process-aware, is the random sampling of time steps during training.
This is what pushes that preference signal back into the early noisy stages.
Yes. Unlike the old models that only see the final clean product, PAVRM learns to judge quality at every single point along the way. It's learning how a good video should be generated, not just what it should look like at the end.
Which brings us from modeling the reward to actually using it. The Process Reward Feedback Learning, or PRFL, framework. This is the optimization stage.
And this is where the efficiency engine really kicks in. The optimization happens entirely in the latent space. You sample an intermediate noisy state, $60, you get the reward score from PAVRM, and you apply your gradient right there.
So you completely skip the VAE decoding step.
Completely. It's eliminated from the main optimization loop. And since you're not pushing gradients back through that massive memory-hungry decoder, the whole system just becomes orders of magnitude more efficient.
And they built in a safeguard against reward hacking, right?
Yeah.
Where the model just learns to trick the reward system.
They did. They use a balanced approach, alternating between optimizing for the process reward, that's LPRFL dollar, and a standard supervised fine-tuning loss, RLHF.
So the SFT loss acts like a regularizer.
Exactly. It keeps the model grounded in reality, maintaining its general diversity and quality, while the PRFL part fine-tunes it for those specific human preferences, like better motion.
So by staying in latent space and sampling across the whole process, PRFL gets that crucial guidance to the early stages where structure is born.
And the numbers on efficiency are just undeniable. In their tests, the old RGB method crashed with out-of-memory errors on the full 81-frame sequences. It couldn't do it.
And PRFL
handled the full 81-frame sequence using a totally manageable amount of VRAM, about 67 gigs. And it wasn't just possible, it was fast.
Up to 1.49 times faster than the baseline, which was stuck only being able to process the very first frame. It's doing more work, faster.
Right, but all that efficiency means nothing if the quality isn't there. But, well, it is.
Let's talk about those quality numbers, especially dynamic degree and human anatomy. A 56-point increase in DD. That's not a small tweak. What does that actually look like?
It's night and day. For a 720p text-to-video generation, you get that plus 56 in DD and over plus 21 in human anatomy. Visually, the baseline videos struggle with weird artifacts. Faces distort, bodies get deformed in complex poses, movements are jerky. Whereas the PRFL optimized videos, you'd see a subject dancing smoothly, maintaining their body structure, moving in a way that just looks physically plausible. And a user study backed this up. Real people consistently preferred the PRFL videos. The motion was just better.
Now, I always love digging into the ablation studies. This is where you learn the real design lessons. The finding about the model depth for PAVRM was fascinating.
It was so counterintuitive. You'd think more layers, more information, better reward model, but nope. They found that going beyond the first 16 DIT blocks actually made performance worse.
It got worse. Why would using the full 40 blocks be worse than just 16?
It seems to be a focus problem. The later layers from 17 to 40 start to focus on really high-frequency model-specific details. You could almost call them the model's latent fingerprints.
And that's just noise for a high-level quality judgment.
It's overfitting. The reward model starts memorizing the generator-specific style instead of learning universal principles of good motion. The core structural information is all in those early and middle layers.
That makes a lot of sense.
Yeah.
And what about the sampling strategy? Early versus middle versus late stages?
They found a clear division of labor. The early and middle stages were crucial for dynamic degree, the big movements, the overall flow.
But the late stages?
The late-stage sampling was what really improved human anatomy. The fine-grained structural details, making sure a hand looks like a hand, that gets finalized in the cleaner later steps.
So you need the whole thing.
You absolutely need full-range sampling. You get the best of both worlds. Early signals for dynamics, late signals for structural refinement.
Okay, last thing. Generalization. They tested their reward model, trained on one video generator, on outputs from totally different models it had never seen before.
And it worked surprisingly well. It learned universal cues about what makes motion look good, not just cues specific to one model. But here's the really interesting part.
Go on.
The generalization was stronger in the high noise regions, close to t=1, than in the clean, nearly finished regions.
Wait, so it's better at judging an unseen model's output when it's mostly noise than when it's a clean video. Why?
It's those latent fingerprints again. When a video is almost finished, its latent representation is full of high-frequency details that are unique to the model that made it. The reward model overfits to the fingerprints of the model it was trained on.
But in the high noise regions,
all those model-specific details are gone. All that's left are the fundamental structural and motion cues. And those cues, like that arm is bending the wrong way, are universal. They generalize across all models.
That's fascinating. It really reinforces this entire idea of process-level reward.
It really does. I mean, the core contribution here is a robust, efficient new way to do video alignment. By staying in the latent space, they've sidestepped the hard limits of pixel space optimization.
This kind of efficiency, especially being able to handle long, high-res video, feels like a necessary step to really advance RLHF for video.
It's the prerequisite. You can't do complex reinforcement learning if every step is this computationally expensive.
So it sets up a really interesting challenge for what's next. This paper focused mostly on motion quality. But now that we know latent space optimization is so powerful, you have to ask, how could you build a hybrid system?
That's the billion-dollar question, isn't it?
How do you incorporate other kinds of feedback like aesthetics, cinematic style, maybe even complex semantics across that latent path without losing all the speed you just gained?
That's the next frontier. You could imagine a layered reward system. Maybe you use these efficient latent-based rewards for structure and motion in the early stages, and then maybe you apply a very targeted, lightweight RGB-based reward for aesthetics only at the very end. Designing that kind of multi-aspect framework is the big challenge for the next generation of these models.